Hey, so I thought I would show people what I've been doing recently towards my little sailing game. Obviously, for a sailing game, you need to have something to sail around. So I'm making the train system to start off with. And because obviously I am a crazy person, I'm basically trying to do this from scratch. So I'm using 3 as the renderer, but otherwise I want to write everything train system, physics, water, buoyancy, blah, 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 all myself because I have the time and the freedom to do that, and it's interesting, and it's great to stop and visit some of these problems. So I'm writing a game, not in an engine, so I'm not doing this in a generalized way. I'm doing it specific to the problems that I'm trying to solve. But other than that, I'm having a great time actually solving some problems. So for this is basically trying to come up with some kind of acceleration structure for collision with the terrain that would work nicely for most things that I want to do with it. So like the first thing I need to do with my terrain is make an editor so I can edit the terrain. And to do that, I need to raycast against the terrain to figure out what I'm trying to edit. So I want something that's reasonably fast to raycast through. But I also want to be able to use it then for, say, doing capsule collision or sphere collision or any other kind of collision that you might want to see in such a game. So I want it to be capable of doing more than just raycasting. And so the kind of structure I've come up with is somewhat obvious. It's a quad tree. That's a very traditional way of spatially partitioning terrain. But I've done a couple of things which I think are quite interesting, primarily to make things a little bit faster. Obviously, terrain is also three-dimensional. Yeah, so the first one of those is each partition of the quad tree stores its AABB, the axis aligned bounding box. And it does that because then you can test against the bounding box. So it's like a bounding volume hierarchy, but obviously with a very fixed size in terms of depth and width for the actual bounds themselves. And that works well with terrain data because it's obviously very uniform and grid-like anyway. And then the second part about it, which is more specific to the raycasts, is that quad trees and the octrees and so on are gridded. They are, and particularly with this sort of data inside a quad tree, it is very much a grid. And so it shares a lot in common with voxel systems, only hierarchical from that sense, although obviously you might put voxels into a sparse octree or something similar to that. So from that perspective, I want to accelerate my raycasting by avoiding doing as much work as humanly possible. And because array that your testing has a fixed direction coming into this grid, and each level of the grid is a fixed size, you can actually analytically know how to step through that grid. And there's a paper written by Amanatides Wu, which implements this algorithm. It's really, really straightforward. It basically boils down to using the equation of the line and working out where the next intercept points are and testing to see which one of those is closest and stepping in the direction of the closest intercept. And the really nice thing about that is that you can pre-compute a bunch of this information before you start stepping through the grid. So the actual steps themselves boil down to a compare and 2 adds, which is pretty fast as it goes. So this is basically what you see in front of you and what's happening. I just give some context. The red, blue, green, yellow is the hierarchy. Each of the intercept points here in these boxes is where there's been a successful ray bounding box check. And then all of the boxes that don't have the crosses next to them are things that have been walked by the voxel traversal algorithm. And then it boils down to, in this case, essentially 1, 2, 3 successful raycasts against the boxes, and then checking these 16, is it 16? 1, 2, 3, 4, no, these 8 triangles finally. And so that's actually really, really cheap as far as it goes. This is 16 by 16, so it's 512 triangles in total. Not a nightmare to test by any means, just in a brute force sense, but obviously the train is going to be bigger than this, and we'll need this acceleration structure in place to actually tackle that. And there's a bunch of other optimizations that I could put into this as well. So for example, you can see in this case, it's checked the full tile of triangles before it's found a hit. And we could definitely do the same voxel traversal algorithm on the quads here and just test the minimum set of triangles based on the quads that you would walk through. It's probably pretty easy to add. I just got to the point where I didn't need to do that. This is also all in one loop right now, so for the voxel traversal, you can split out variants and avoid a bunch of branching that way, but again, isn't necessary for my use case. It's just, it feels like a really neat approach in general. And like just to talk through what's going on here for the hierarchy stuff as well. Obviously, I'm hitting this point on all 3 of the external bounding boxes. And then because this is being looked at as a flat thing, it's now testing against the internal one, this yellow one here, of this containing set. And it doesn't hit it, so it needs to step basically into the next location for this. And in this case, with the direction of the ray, it's either going to step forwards or it's going to step sideways. But both of those will step outside of its containing bound. And at that stage, we move up a level and we do the step again. And in this case, it steps into the green section here. Ray doesn't hit it, so it does the algorithm again. And in this case, steps sideways. Ray does hit it, so it steps down a level. Ray doesn't hit the first thing that it's in, so that it steps forwards again because of the ray direction, and then steps sideways again, and then finally hits the containing thing inside that bound. So it's very, very, very efficient in that sense. I don't know if this is a novel implementation approach at all. All of this stuff I've basically gone from a perspective of wanting to implement it myself without looking at other people's implementation of things, and without looking really at like the detailed versions of these things. Like the Amanatides Woo paper is very light on the details of how you actually step through things, so it's pretty fun to work that out and apply it to a hierarchy as well. There's probably a bunch of other fun things you could build on top of this, but that's what I've made. And then the quad tree and the AABBs just make it really easy. If you want to like test the sphere against things, you're obviously just doing the classic walk down the tree to see which bounding boxes you're within. And in this case, it can take advantage of the fact that things are 3-dimensional with the bounding boxes stored there. Implementation wise, it's pretty long right now and full of debuggy cruft. I need to go through and tidy this up. But yeah, like the actual thing is all done in a typed array or several typed arrays to keep things tight in memory, and then just storing a few extra bits and pieces in order to walk back up and down the tree. So it's pretty quick from that perspective as well. Anyway, that is the joy of what I've spent this week doing.